Okay, let's continue the discussion. In the next theorem, we're going to discuss the so-called monotone properties. Monotone property. So what is a monotone property? Assume we have A, a subset B, are non-empty. Subsets of R. So here I emphasize this non-empty is very important because after the theorem we will have a little bit remark about this supremum and the monotone property. You will see that if there's no non-empty condition, some strange phenomenon can happen. So for a pair of non-empty subset A containing B, if B has a supremum then the supremum of A is less than or equal to the supremum of B. So this is what the monotone means. The supremum of a subset is less than or equal to the supremum of the superset. B, if B has an infimum then the infimum of A is greater than or equal to the infimum of B. It looks like the supremum is an increasing function. For the superset, supremum is bigger, but the infimum is a decreasing function. For supremum, infimum for the superset, the infimum is smaller. Okay, a bigger set, smaller infimum. Okay, so the proof is not difficult. It's a very simple. Let's see the proof. For the first part, A is contained in B, then any upper bound of B is an upper bound of A. You have an upper bound of B because it's already very big, it's bigger, so the upper bound of B is a upper bound of A. Therefore, supremum of B, super B is an upper bound, is the smallest upper bound, right? So the super B is an upper bound of A. It's just the conclusion of this previous result. Okay, and then by the completeness, axiom, the supremum of A, super A exists. Okay, so what is a completeness axiom? Completeness axiom says for the subset of real numbers, if it has upper bound, it will have a supremum, right? Okay, so B is the upper bound, so upper bound exists, then the supremum A exists, and supremum of A is the smallest upper bound. So the super A is going to be less than or equal to whatever upper bound. Super B is one of them, so super A is less than or equal to it. right? So that's the case. That's a proof, you see. So here you have to claim first, super B is an upper bound, and second, completeness axiom implies the existence of a super A, and then by the definition of supermom, you get super A is less than or equal to one of upper bound super B. All right? Okay, so now let's talk about the infimum. In this process, you can see that this is a definition of upper bound. This is a definition of upper bound. And this is a property of real numbers, completeness axiom. And the completeness axiom is related to the supermom. Of course, we can get the counterpart of the completeness axiom for the infimum, but in order to keep the system of postulate as simple as possible, so we only list the completeness axiom for the supermom and don't include the corresponding result for the infimum. But actually, we have the similar statement. If it has a lower bound, then the infimum exists. It's the same thing, but we don't consider it as a part of an axiom. So in order to almost copy the above statement, we need the completeness axiom. So we still need the supermom. We still need supermom. How do we do that? We get the negative A as a subset of negative B. A is a subset of B. The negative A is a subset of negative B. Then by part 1, we have the sup of negative A is less than or equal to the sup of negative B. Right? We just proved the sup part. Okay? And sup negative A, we already discussed, or we already computed. It is equal to the negative inf A. Sup negative B is equal to negative inf B. Alright, so you get negative inf A is less than or equal to the negative inf B. This is equality, just do the substitution. Multiply this inequality by negative 1. You get the inf A is greater than or equal to inf B. So everything is done. Okay, so we transform the infimum problem to the supermom problem, but you have to use negative A instead of original A. Okay, so the discussion of the supermom and the infimum are valid, are possible only for the non-empty set. Okay, remember it's for the non-empty set, and also we want to consider the so-called bounded set. One is non-empty, the other one is bounded. So to consider sup A inf A, we need non-empty and bounded set. Of the real numbers. Why we need an empty? We always put an empty here. How do we get the bounded? If it has upper bound, it's bounded from above. If it has a lower bound, it's bounded from below, right? Bounded means it has bounded from above and from below. In this case, by the completeness axiom, we can get the supermom and the infimum. And now we want to drop these conditions. We want to discuss the supremum and infimum for all sets of real numbers, not just non-empty bounded set. In order to do that, we need an extended real numbers. Okay, so extended. An extended real number x means either x is really a real number, or x is a negative infinity, or x is a positive infinity. Okay, so we try to add the right end and left end. Right end, when I say right end, we mean the positive infinity. When we say left end, we mean negative infinity. And you see, when we get the number line, direction, origin, unit, then this part, the right end is positive infinity, left end is negative infinity. So we try to just add these two additional points. And then let's try to discuss so-called the infimum and supremum for the unbounded set. Okay, so when we talk about unbounded set, it's still non-empty, right? Let E in R be non-empty. Non-empty, then we define non-empty, then we're talking about unbounded. Unbounded, there's some three possibilities. One possibility is it is not bounded above. The other possibility is not bounded below. The third possibility is neither bounded above nor bounded below. So three possibilities. So let's discuss them one by one. If E is not bounded above, is not bounded above, or you can just say unbounded above. If it is unbounded above, we define the supremum of E to be positive infinity as large as possible. Okay? So this is the first case. And second case, if E is unbounded below, then we define the inf of E to be negative infinity. Inf of E to be negative infinity. If E is unbounded above and unbounded below, then we will define sup E as a positive infinity and inf E as a negative infinity. Right? So just combine the first two cases, you will get the third case. Okay, so this is one of a direction to extend the sup and inf. The other direction, empty set. Here's non-empty. For empty set, we define what? We define the sup of E to be negative infinity and inf of E to be positive infinity. This is the most strange part. Okay, this is the most strange part. Because in the common sense, you see, in the common sense, for a subset 0, 1, interval 0, 1, this is a supremum. This is infimum. At least we know that the supremum is greater than or equal to the infimum. This for non-empty set. It's very important that non-empty. The sup E is greater than or equal to the inf E. But here you see that the supremum E is negative infinity, infimum E is a positive infinity. Clear negative infinity is less than the positive infinity. Why do we do such definition? This definition comes from this monotone property. What is a monotone property? Monotone property says for any subset, if it's non-empty, then the sup A is less than or equal to the sup B. All right? And we know that the empty set belongs to whatever set. Whatever set. Empty set is always a subset of any set. If we want to preserve, but the empty set is not non-empty, so you cannot get from here. But still, we want to preserve, we want to keep this property. We want to keep this property, we will get the sup of empty set is less than or equal to the sup of A for arbitrary set A. Arbitrary set, then the supremum could be anything. Sup A can be any number. Sup A can be any number, then the sup empty set should be less than or equal to any number, then it has to be negative infinity. So this definition is required or is used when we try to keep the monotone property. Okay? That is the reason we put the negative infinity here. In a similar reason, or with a similar concern, the infimum of the empty set should be greater than or equal to the infimum of arbitrary subset from the monotone property. We just proved that the infimum of a subset is greater than or equal to the infimum of a superset. Empty set is also a subset of arbitrary set, so infimum is greater than anything. And for arbitrary set A, this can be any number. So the inf empty set should be greater than or equal to any number. So the inf empty set equal to past infinity is used for monotone property also. Right? So that's a reasonable stuff. And actually here if we do not just want to preserve the monotone property, the inf empty set or super empty set can be assigned to any number. It doesn't matter. Because how do you say it's not true? Like for example, if we want to say that A is not a supremum. Let me see, how do I phrase it? If A is not sup E, A is not sup E. Let me think about it. Okay, let's see. A is not a sup E. There's two cases. Case 1, A is an upper bound, but not least. Okay, A is the upper bound, but not least. Then there's another upper bound. A prime, such that A prime is less than A. So this is the case. Case 2, A is not an upper bound of E. A is not upper bound of E. There is an element E in E such that E belongs to what? E belongs so E is greater than A. It's not upper bound. Okay, so let's see. But this case can never happen if E is empty. If E is empty, then there is no element E in E with E greater than A. Right? There is no way to get an element because there's no element. There's no element E so that E is greater than A. Hence, any A will be an upper bound. Any E could be an upper bound because if A is not upper bound, then you have to find an element. Since there's no way for you to find an element, so any A will be upper bound. Any A will be upper bound, so this A will be less than or equal to any A prime. Let's say A prime. So A should be less than any number A prime. A is less than any number A prime, then A has to be negative infinity. Right? A has to be negative infinity. So from the definition of a supermom and the supermom, we can also get it. And in a similar argument, so here it might be a little bit math. Let's use this process to do to discuss infimum. To discuss infimum, we need the lower bound. So let B be a lower bound of E. Okay, so B is a lower bound. How do you get the negative statement? How do you find a B which is not a lower bound? B is not a lower bound of E if there is an element E in E with E less than B. Lower bound, the smallest one. Here you have element is even less than B. Okay, so this is the negative statement. But if E is empty, there is no element E in E with E less than B. So no such element. Here there is no such element. This is a negative statement of this negative statement. Hence, for any B, B is a lower bound of E. For any B, B is going to be the lower bound. And the infimum is the greatest lower bound. Inf E is the greatest lower bound, then the inf E has to be positive infinity. Okay, so inf e has to be the positive infinity. So that's another way to clear why this is a lower bound and super bound. I possibly say something incorrect. Not every number can be assigned to the super empty set and the inf empty set. Only positive infinity and negative infinity are the proper selection choice. Okay, this is a only unique choice. Sorry. Okay, so this is the discussion of sup and inf. The extended definition of the supermom and the infimum for all subset, including unbounded and including empty set. And be careful, empty set plays strange in a strange way. Empty set, the supermom is negative infinity, infimum is a positive infinity. That's a very, very strange property. Okay. Okay. So we finished this section, and last time I already assigned the exercise for this section. You can do the exercise and try to understand the process. Next, let's talk about the functions, countabilities, and the algebra of the sets. Okay. So for this class, at least for the first few chapters, we only discuss the so-called real-valued function of real variables. So when you have a function f, it's from its domain to the range to the real numbers. Then the domain is also the subset of real numbers. So this is called f is a real valued function of a real valued variable of a real variable. Okay, so here let's talk about a little more about this. So when we have, if you have a function, if you have a real subset, and it is mapped to Rn, like for example, when you study it in the let's this way, change this way, from Rn to R. This one is a multivariable functions, right? Remember that in the calculus 3 you have a multivariable. When you have multivariable functions, you have partial derivatives, right? So multivariable, when the domain is a subset of Rn, it's multivariable. And here we didn't emphasize it. It's also actually a real valued multivariable function. Real valued multivariable function. And if we have the range in Rm also, here the domain is Rn, the range is Rm. This is called the vector valued multivariable function, right? Vector valued, because in this case we consider the element in Rm as a vector valued multivariable functions. And of course, if you learn more, you can replace this the set of real numbers by the set of complex numbers. Then you will have complex vector-valued, complex multivariable functions. Okay, you just put complex there. And you may also replace this to the other type of a function space. So you can replace it by other type of space. You will get other functions. Sometimes in that case, they may not call it a function. You will see the vectors, transformations, whatever way, but they are just play the similar role. All right. And in this book, we only care, or in most cases, we only concern this type of function. This type of function, it is also called just real functions. It's also just called the real function. Real valued, real variable. One value, value is one-dimensional. Variable is also one-dimensional. And in this discussion, we also we are interested in the trigonometric functions, sine, cosine, tangent, cotangent, secant, cosecant. So all 6 trigonometric functions, and we have the natural logarithmic functions and the exponential functions, and we have even power functions, arbitrary power functions. It's not, alpha is not necessarily an integer. So here, a power function can also be defined by the combination of the exponential function together with the natural logarithmic function. And because of this purpose, we always require the power function to have a positive input, alpha is here. So here you have to be careful. When we just get a general power function, the domain is x greater than 0. But if you only consider the x to nth power, then this x could be any real numbers. Okay, so other than integers, this x can be, if it's not integers, x has to be positive. If it is integer, x will be arbitrary set. And also, if you have, for example, x to 1/3 is not integer, still it is possible to define x for define a function for negative numbers. So the domain, the natural domain for the cube root function is still from negative infinity to positive infinity. But in general, if you have nothing to say, or you don't know anything, x to alpha, you don't know anything about alpha, then x has to be positive. Okay, we just try to make this definition clear. And then we will have the same derivative, right? All the derivatives will be the same derivative formulas. And we also have x to alpha has derivative alpha times x to alpha minus 1 from the chain rule. All right? And all these rules or properties will be repeated in the future sections, chapters, okay, in the future. But so far, since those are the algebraic stuff, we will, someplace we may just accept them, but before we prove it, okay? Okay, so we have functions, regular functions. We have regular derivatives. Sometimes we use it, sometimes we don't. And later we will prove all of them. And another thing, after the definition of definition of function, we have that one-to-one function. We also have one-to-one function. Okay, so let's see. Definition. Let f be a function from a set X into a set Y. From a set X into a set Y. Then part 1, f is set to be 1-to-1. Well, here we write 1, 1. On X, if and only if x1, x2 belong to X, and fx1 is equal to fx2, imply x1 is equal to x2. Okay, this is a 1-to-1. And second condition is called onto. F is set to take X onto Y if and only if for each Y in Y there is an X in X such that Y is equal to fx. Okay. Okay, so for example, fx equal to x squared is 1-to-1 from 0 infinity onto 0 to infinity. Okay, it's a 1-to-1 and onto, but it is not 1-to-1 on any open interval containing 0. Whenever it contains 0, you will have a positive, negative. When you have positive, negative, you may have the same value for different input, right? So it's not 1-to-1. And 1-to-1 sometimes is also called injection. 1-to-1 function, injection, or 1-to-1 injective. The property is called injective. The function is an injection. And onto is also called surjective. And together, 1-to-1 plus onto is called bijective. Okay, 1-to-1 plus onto is called bijective. Those properties. Okay, so since we will use this 1-to-1 and onto properties a lot, let's see some simple discussion about those properties. So 1.31, we have a theorem. So let X and Y be sets, and f from X to Y, so you have a function, then f is 1-to-1 from X onto Y if and only if there is a unique function g from y to x, onto x that satisfies two conditions. Okay, so which two conditions? Condition 1, f g of y is equal to y for all y in y, and g of f of x is equal to x for all x in x. Okay, so the one-to-one and onto the bijection is equivalent to the existence of such function g. Now let's prove the equivalence. So suppose that f is one-to-one and onto. F is one-to-one and onto, then for each, we are going to define g, function g, with those properties. For each y in the image set y, we are going to define it. How do we find the image? Choose the unique x in x such that fx is equal to y. So it is onto, so there exists x so that fx is equal to y. It's a one-to-one, there is a unique one. So one-to-one give us uniqueness, onto give us existence. You have unique one with this property. Okay, because this is unique, you can have the fixed target. Then we define g of y to be this x. Define this, and it is clear to see that g takes y onto x. It is onto, and g is one-to-one. We don't need one-to-one, we just need onto. Yeah, and g satisfies those two conditions. Okay, so g satisfies the conditions. How do we know g satisfies the condition? We know g of y is equal to f if f of g of y is equal to x if f of x is equal to y. Then f of g of y is x, so it's fx is y, so it's a combination. And the other way, g of f of x, fx is y, g of y is x, gy is x, so g of y is x. So we just verify those two conditions. Okay, so from one-to-one and onto, you can define and prove the properties for this unique function g. Let's see the other way. Conversely, suppose that there is a function g from y onto x that satisfy those two conditions. Those two conditions we mean here. Those two conditions. Now we want to show f is one-to-one and onto. So we are going to show f is one-to-one. let x1, x2 be from x, and fx1 is equal to fx2. fx1 is equal to fx2. Then what we have? Okay, so x1, where is x? x1 is here. It's a g of f of x1. G of f of x1 is the second condition. And fx1 is fx2, so it's a g of f of x2. And g of f of x2 implies, but still by the same property condition, it is a gf cancelled, you get x2. So you first have x1 is equal to x2, f is 1 to 1. F is 1 to 1 on x. And second, we're going to show f is onto. So for any y in y, choose any y in y. Let x be g of y. X be g of y. Then what we have? We compute fx. Fx is f of g of y. But fg of y is y. So y is the image of x under f. So f takes x onto y. Okay, f takes x onto y. Well, so here this condition, well, this is converse. And this place, whenever you have such g, you can prove f is 1 to 1 and onto. And you also need to show this g is unique. Okay, so next we assume g, we want to show that g is unique. There is a unique g. So suppose h is another function that satisfies those two conditions. We want to show this h is equal to g. Okay, so let y be an element in the set y. Choose x in x such that fx is equal to y. Fx is equal to. All right, then let's continue. By the condition, by the second condition, h of y. H of y. What is h of y? H of y. Y is fx. H of f of x. H fx, the second condition, it means it's equal to x. But we know that g also satisfies this condition. G also satisfies this condition. So x is equal to g of f of x. And g of f of x, fx is y, so it's equal to g of y. Okay, so it implies for every value, every y, g of y is equal to hy. So h is equal to g. Then g is unique. G has to be unique, right? So after this verification, this is straightforward. After this verification, if f has if f is 1 to 1 from a set x onto a set Y. It's if it is one-to-one from set X onto set Y. In other words, a bijection. If F is a bijection, we will say that F has an inverse function. F has an inverse function. And the function G in the theorem is called the inverse. Because it's unique, so you say the inverse of F. Inverse of F. And we write G of X equal to F negative 1 of X. So here there's a small writing issue. If you write Fx and parenthesis negative 1, this means the reciprocal. If you write F negative 1 of X, this means inverse. So be careful about the difference of those two writings. They have different meaning. All right? Since G has a unique symbol, F inverse, F negative, so you may write F negative of Y equal to Y and F negative F of X equal to X. So those two are both identities, but they're slightly different. This is identity on Y. This is identity on X. Okay? And from the calculus, we know that if we have a function, numbers, let's assume we have numbers, a real number, a real function. Then we can get the point x, fx. It is on the graph of f. And what else? And we also have that x is inverse of f, and if we call this fx, if we call it y, then what is x? X is f inverse of y. Then this is also on the graph. Okay? It is also on the same graph. If you write it this way, nothing changes. But if you write y, f inverse of y, it is on the graph of y equal to f inverse of x. Or the other way, x is equal to f inverse of y. It doesn't matter. Okay? So if you exchange the positions, if you do not exchange the position, you just change the symbol, nothing changes. This is still on the graph of y equal to fx. So this is still on the graph, the same thing. You just change the expression. But when you interchange the positions, it is on the graph of y equal to f inverse of x. And we will stop this video and continue in the next video. From next video, we will discuss the relation between those two graphs. The graph of f and the graph of inverse of f. Okay, so we finish this video now.